So I'm presenting on AWS VPC, which is both an acronym and also an Amazon product, so it can get a little confusing, but I will cover that in a moment. So about me, my name's Wyatt. I work here in Winnipeg for Manitoba Blue Cross full-time. Started doing Linux primarily. Then I started doing network administration, firewall administration, and now I'm doing cloud administration, which sort of encompasses the Linux and networking work that I was doing prior to that. Also, some of you might know me. I'm president of the Manitoba Unix user group. We have a meeting once every month here in Winnipeg, usually on the second Tuesday of the month. So that was yesterday. So we had a meeting at the U of W yesterday. So if you're interested in Unix, Linux, open source, you should check us out. It's muug.ca and come to one of our meetings there. So what is VPC, or Virtual Private Cloud? Well, VPC stands for Virtual Private Cloud, and it's simultaneously a paradigm, aka Virtual Private Cloud, but it's also an Amazon product, that is VPC. So when you're referring to VPC, don't get confused between the Amazon product, VPC, and the paradigm, which is Virtual Private Cloud. They're the same, but they're different. So you have to know which one of those you're actually talking about. And in this context, I'll be primarily, anytime I say VPC, I'm specifically talking about the networking object in AWS that is VPC. So Virtual Private Cloud on its own is typically hosted infrastructure where you can do things the cloud way, that is using APIs to dynamically create infrastructure. Programmatically, you're not going in and you're not plugging in hard drives, you're not running network cables. It's all cloud. So that's the idea behind Virtual Private Cloud. Some people would say that private cloud specifically would refer to hardware that you're still managing, whereas public cloud, which is typically what you would call Amazon, is infrastructure that someone else runs, and then you pay them a service fee for that. So some people might say that Amazon is misusing the term, calling it Virtual Private Cloud, because it's not really private. It's private from a networking sense, but it's not private that you control it 100% from top to bottom, full stack. So like I said, VPC is a provisioned AWS object. So when I'm talking about VPC, it's going to be the networking object. I'm not talking about Virtual Private Cloud as a paradigm. So moving on to the history of networking in AWS. Way back when AWS first came up with the idea of, or rather, when Amazon came up with the idea of AWS, that is Amazon Web Services, they didn't have private networking at all. They have what's now called AWS Classic Networking. And Classic Networking was basically what you get with a traditional VPS. If any of you guys buy servers from DigitalOcean or OVH, normally an old-fashioned VPS will give you a preset virtual machine that's running, and it's going to have one public address, and that's the only connectivity you have to it. So everything you do over the internet. We'll give you a key to get into it, and other than that, all your network traffic to this instance that you're paying for is going over the internet. So in 2009, they changed that, and they introduced their product, which was AWS VPC, or Virtual Private Cloud. And VPC networking was their solution to allowing you to create private networking within their hosted environment. As well, they also added the function of VPN tunneling built in. So a private network isn't very good if you can't route to it. So if you have a private network in your own data center, obviously you're already connected to it. But if you have a private network off in the cloud, well, how do I actually get to it? They offer a feature of built-in VPN tunnel, so you can actually provision that, and then you've got private networking between the virtual network that's in AWS and your on-prem networking as well. So what is a VPC? Well, we talked about virtual private cloud. Now, what is the actual VPC that you're going to be provisioning in AWS? So essentially, it's a provisioned private environment where AWS resources will be deployed. And it gets a little weird because everything you do or a lot of things that you do in AWS involve your VPC. So it's easy to think of it as being inside the VPC, but it's more like attached, which can be confusing to think about in your head. But you're basically associating your resource with your VPC, and then AWS knows behind the scenes how to actually connect your networking together and put it into your VPC. So VPCs define a private network space that you're going to be working with. It's essentially you're signing a block of IP, and then those IPs will get assigned to the resources that you're creating. You can sort of think of a VPC like a data center in the cloud in terms of networking. You're going to have a lot of the same components. You're going to have different subnets. You're going to have routes between them, and you're going to be able to determine traffic flows with that. And also, you'll see a lot of common terms as we go through. You'll see things like subnets, route tables, gateways, endpoints, and those are all very familiar networking terms if you've ever worked on network hardware before, but they're not quite the same in AWS. So you might think, oh great, they give me a gateway. Well, I know what that is, but it's actually different in AWS. So you have to go through each object that you're working with, and you actually have to learn about, well, what's the AWS version of this traditional piece of infrastructure that I was already used to working with. So continuing on, getting more technical, the VPC is defined with RFC 1918 CIDR ranges. So that's anything in 10.0.0.0/8, 172.16 to 32, and then 192.168/16. So those three private IP ranges can be used on a VPC. And the maximum size that you can use from one of those is a /16. So even though with the 10.0.0 IP space, even though you've got /8 to work with, you can only allocate /16 of that into a single VPC. So when you're looking at creating VPCs, the maximum number of addressable objects you can have in that VPC is going to be 65,535,000, which is /16. Technically, you can reuse those CIDR ranges between your VPCs. So if you say, oh, well, maybe I want two networks to both have 10.1.1.0, you can do it. They'll let you do it because they're completely isolated from each other. And obviously, every customer is using the same private IP ranges. So they have to support it. Typically, it's not recommended unless you actually run out of IP addresses that you need to start reusing them. But there's times where you do interconnect your VPCs to each other, and that's where you could run into an IP address conflict where you need to be uniquely addressed within your own resources. So if you can avoid it at all, don't ever reuse IP ranges between VPCs. There should be enough that you can avoid that. And you also have to consider local IP address conflicts as well. If you're connecting over a VPN to your on-premise networks, same thing there. You have to have unique IP spaces. So if you've used up all of 192.168 on-prem, then you can't use any of those in your VPC. Otherwise, the routing doesn't work between them. And at its core, VPC is software-defined networking. So at the very lowest level, there are probably routers and switches, but it doesn't behave like that. And you shouldn't think of it as a network switch or a network router because realistically, it doesn't behave like that. So it simplifies certain things. You can very easily change routes. You can add network devices, and it all happens instantaneously because of that software-defined networking. But at the same time, there's limitations to that where you'd think, oh, well, if this was a traditional network, I could just hook this, and this up, and the traffic would go where I want it. And you try and do that in AWS, and it just doesn't work. They just drop the packets because they can't do what you're asking it to do. So you have to be mindful of that. That's bitten me a couple times where I think, oh yeah, I'll just put a virtual firewall up and I'll route traffic through it. And nope, you can't actually route traffic the way that you thought you could. So you have to be aware of that and do some trial and error if you're worried about that. So in each VPC, we're going to divide the network up into logical subnets, which don't really actually matter. It's more about logical organization within your network. So the subnets are allocated out of that CIDR range that you create the VPC in. So if you allocated a /16 for your VPC, then each one of your subnets will be variably subnetted out of that /16. So you can create, I don't know off the top of my head what the minimum size is, but you can create 28s? Okay, there you go. So you can create 28s, and you could create whatever it is, like 1,000 /28s out of that /16 if you wanted to divide your network resources up into small little chunks like that and say, each one of these blocks of IP addresses have a separate function, so that's why we want them divided. Or you can just run /24s like most people do for typical network zones. And then you'd have, in that /16, you'd have up to 254 subnets that you can create. Yes. So they don't provide any actual isolation. So if you're thinking of a traditional network where you had a router in between your subnets, you might think, oh, well, I'll just tell the router, don't route between those two subnets. Well, Amazon won't actually let you do that easily. There is no way to create two subnets in a VPC, and by default, every subnet can talk to every other subnet. So if you're creating subnets thinking, I'm going to use subnets for my security and I'm going to just not connect all my subnets together, well, it doesn't work. You have to explicitly deny subnets connectivity to each other if you're worried about that. And then route tables are logical connectivity between, logical definitions of where traffic is going to flow between your subnets. So again, a route table is something you might have heard of on a traditional router, but here it's a virtual object that you attach resources to, and those resources will then automatically be routable through that route table. So that's where the software-defined networking really comes in, is you can just attach objects, you can attach subnets to a route table, and the traffic is just automatically flowing. You don't have to specify IP ranges. You don't say this subnet at this subnet mask with this gateway, put that route into my route table, and then it'll connect. All you do is you attach your subnet to your route table, and it just works. Now that route table, now that subnet is routing through all of the objects that are connected to that route table. And like I said, yeah, no IP addresses are ever used. In your route table, it's all object identifiers. So let's talk about DHCP. Another thing is DHCP is turned on, and so is DNS. So if you're used to a normal server network where you'd say, no DHCP, we need to statically IP every computer that's on our network. That way we know every single address of every single computer. You don't want to do that in AWS networking because it doesn't scale at all. And ideally, you're going to be deploying resources with automated tools, and you want those tools to just get an IP. Whatever IP is available in your subnet, it's just going to grab an IP and it's going to get handed out by the internal DHCP service, which just exists in your VPC. So there is no DHCP server enable. There is no instance that provides DHCP. It's just an internal function of the VPC that gets provided. As well, there's also an internal DNS resolver as part of your VPC. So it's the second address in your VPC. So there are certain Amazon functions that have reserved IP addresses in your VPC, and they provide certain functions. So at the .2 address in your VPC, or the second usable address, is this DNS resolver that's just there, and it answers queries. But you don't actually see it anywhere. If you go into your VPC config, again, there is no DNS server button. There is no instance. It's just an IP address that if you send it a DNS query, it'll respond back, and it'll give you a name resolution. So just recently, actually, they came out with a real name for this, and they're calling it Route 53 Resolver, and they've added some functionality to that as well. But for the time being, or for in the past, it was simply providing recursive name resolution, as well as it allows you to resolve a Route 53 hosted zone that's associated with your VPC. Back onto DHCP, so you get a DHCP scope automatically. Again, you don't define that. Every time you create a subnet, the subnet comes with a DHCP scope, which is the subnet. So there is no, you don't have to worry about defining that. The entire subnet is DHCP in scope, and it is smart enough that if you do give it a static IP address, it will pull that IP address out of the DHCP pool. So you can statically address, you can mix and match, and you can say, well, this is just a test box. So I always want my test box to have, .99 or .254. So as soon as you boot that machine up, it's gonna detect that IP address is in use, and then DHCP isn't going to hand out that IP address anymore. But if you turn that instance off and you let it sit, and then you boot up another instance that's dynamically asking for an IP address, the VPC will go, okay, take that IP address that was being previously used. It's not being used anymore. So there's no way to reserve a DHCP address like you would in a traditional DHCP server. All addresses are up for grabs anytime they're free. So like I said, the best way is to always do things dynamically, and then you rely on DNS to actually resolve those dynamic addresses that you're getting. So if whenever you're getting an address, it's also being registered with DNS right away, and then you use those DNS addresses to actually find out what the IP address of the instance you created was. So I'll talk about gateway devices. So gateway devices are a special class of objects in VPC networking. And again, you might be thinking gateway, oh, well, that's .1 or that's .254, where I send all my traffic that isn't in my local subnet. Well, in AWS, that doesn't exist. So gateway devices are special devices which provide connectivity out of your VPC into different types of connectivity. So whereas traditionally on a network you might have a firewall or a router that does all your network address translation if you have some external IP addresses, you would then give them to your router and you would configure NAT. Well, here they have a special gateway called a NAT gateway, and it does NAT, and that's all it does. Or they have an internet gateway, and the internet gateway is probably the most abstract of them all. It actually doesn't do anything. You can't talk to it. It doesn't have an IP address. All it does is it tells Amazon, it says, hey, any machine in this network that has a public IP address, let traffic in and out of the internet to that IP address. So each of these gateway devices are one of the things that get attached to a route table in your VPC. So when you're creating route tables, you say, okay, well, there's certain subnets that are connected to this route table. These subnets need to get out to the internet. Well, I need to attach an internet gateway to that route table in order to route to the internet. So that's where that dynamic assignment comes in, and you say, you don't have to worry about IP ranges or gateways or routing. You just assign the resources that you've created to one another, and traffic just starts flowing. So as long as you have the right objects connected to each other, the traffic starts flowing. You don't have to worry about IP addresses. It's all just unique IDs in AWS. They also offer a egress-only gateway, which is sort of a special IPv6 object, because hopefully you don't need NAT if you're running IPv6. There's no such, or Amazon doesn't let you use private IPv6 networking. They always use public ranges when they assign IPv6. So they do offer a built-in device that instead of having to worry about firewall rules on every single host trying to say only allow outbound traffic. They just give you a special device that does that automatically for IPv6. And then with IPv4, they offer that through the NAT gateway. And then there's also the virtual private gateway, which is part of the VPN that I was talking about. And so the virtual private gateway is how you actually add that connectivity to your route table, because everything has to, in some way or another, connect into your route table in order to allow Amazon to actually interconnect the different networking components together and actually route traffic. So if you're running virtual private cloud, by default, you don't have internet. And so you might not want your instance to ever have internet. And you might say, well, wait a second, I'm hosted by Amazon. I should be able to talk to all of Amazon's services directly. Like, why would I talk to the internet to get to S3 if I'm hosted by Amazon? So if you were to use one of the gateway devices that I was talking about in the previous slide, and you were to query the Amazon API, you'd be going over the internet, and you're paying Amazon internet bandwidth prices in order to do that. So even though your instance is in AWS, if you upload a large file to S3, you're actually going back out to the internet and then coming back in the same spot, and you're being charged for all that round trip bandwidth through their internet pricing, because you don't have a way to actually talk directly to Amazon. So that's where endpoints comes in, and endpoints allow you to create another virtual device which sits in your VPC, and it gives you a direct connection to various parts of the Amazon API. So they're all basically individually broken up. There's a list of them that you can get based on the different services. So there's an S3 endpoint, there's a DynamoDB endpoint, there's Secrets Manager, logs endpoints, and they allow you to talk directly to Amazon privately in your VPC without ever having to go on the internet. So that's more secure, and it's also more efficient. If you're moving high volumes of data, you want as low latency as possible and direct connectivity into the Amazon API. So endpoints let you do that. And they come in two flavors. The first is a gateway flavor, and the second is an interface flavor. And the first one, gateway, gets attached to your route table. So that's another object which is put into your route table. And as soon as you put that object into your route table, it's changing how traffic is routed between your subnets. And what it's actually doing is it's saying, oh, you're trying to talk to s3.amazonaws.com. Well, that resolves to this public IP address. Well, I'm going to pretend like I'm routing that to the internet, but I'm actually going to route it directly into the Amazon core network. And the command line or whatever is making that API call is none the wiser. It doesn't know that it's not talking to the internet, because that networking layer in the VPC is just redirecting the traffic to this virtual endpoint. And that's enabled through the route table. So if you only put that gateway device in a certain route table, but not in another route table, well then, depending on which subnet is connected to which route table, you can actually, that's one of the ways you can use this to control your traffic flows. And you can say, well, these should talk to the endpoint, but these never need to talk to the endpoint, so don't connect them, don't make things overcomplicated, just leave them disconnected from that endpoint. The other type is an interface endpoint, and the interface endpoint doesn't do that fancy routing trickery, and I'm not sure why they're different. It's obviously a limitation on AWS's end with which way they're able to implement them. And so what the interface endpoint does is it actually takes an IP address in your private network in one of your subnets, and you talk to that IP address instead of talking to the public IP address of Amazon. And so you might say, well, how the heck do I specify an IP address when I'm making an API call to a DNS address? Well, they do another sneaky trick, which comes in with that Route 53 resolver, which I talked about earlier, is they secretly change the DNS record of the API that you're querying. So instead of it happening at the route table, it happens at the DNS level, and they say, oh, you want to talk to logs.aws, amazonaws.com. Well, the IP address for that is actually this local VPC address right here, and you know how to route to that. So that relies on using that resolver service local to the VPC. Because it is possible to run your own DNS in a VPC. You can boot up Bind, or you can boot up Active Directory if you hate yourself. And you can run your own DNS zones and do your own resolution. But one thing you'll lose is you'll lose some of the special functionality that using the native name resolution in your VPC provides. And I think that's it for that. So now on to security groups and NACLs. And Muzz talked about this in his EC2 talk a little bit. So what is a security group? Well, a security group is, you can think of it sort of like a virtual firewall that gets applied at the resource level. And when I'm saying resource, I mean essentially it could be an EC2 resource, it could be an endpoint resource. There's actually quite a few different Amazon resources that you can assign security groups to. And so a security group is essentially a stateful firewall that you create firewall rules in that allow traffic through. So by default, a security group has a drop all. They don't actually call it drop all. You don't see it. It's just that hidden rule that's at the very bottom of your list that you can't see is essentially just saying, if there isn't a rule for it, just drop it. Don't respond. Don't do anything with it. It just gets dropped. So the only thing that you're actually adding to your security group is allow rules. You don't have to worry. In fact, you can't add a drop rule. So if you want to say, oh, well, there's one machine, I never wanted to talk to these machines, so I'll just add a drop rule in my security group on that one machine, and then it won't be able to communicate out. That's not a capability of security groups. They're only creating allow rules. So in order to do something like that, you would have to actually limit your allow rules in that one specific group to be more strict, and then rely on that drop all, that anything that isn't matching the allow rules is then going to get dropped. So like I said, security groups are stateful, which for those of you who don't know, that means that any packet that comes in, when the host replies to that inbound packet, the security group is automatically going to know that it should be allowed out because you allowed it through. So you don't have to say, you don't have to make corresponding inbound and outbound rules for all the traffic that's going through. It is stateful. If your traffic is inbound first, initiated from an external client into your host, then all you need is those inbound rules, and vice versa. If you know that you're not allowing any inbound connections, you're only allowing outbound connections, then you allow that outbound rule to initiate a connection, and then that return traffic is automatically going to be allowed back in. You don't have to create any allow rule for that. So security groups are reusable across resources, which is very handy. So if you let your security team decide what security groups are allowed to be assigned to what objects, you can make one security group that says only allow SSH. And then you assign that to all of your servers, and you know that while this one security group has been audited and approved by a security officer of some kind, and they know that, yes, we acknowledge that this port is allowed to be open, and yes, you're allowed to assign this to your instances to provide that network connectivity. They also stack together. So if you have, instead of saying, oh, well, this one server needs these ports, but this other server needs those ports and more ports, and then this server needs a different subset of ports, well, instead of making a unique security group for every one of those different use cases, you can make a security group for each service, if it's one port or if it's a collection of ports specific to a service, and then whichever combination of those services is on the host that you're working with, those are the security groups that you would apply. So if you've got a web server that needs SSH and port 80, you would assign your SSH security group and your web security group. And then you don't have to create a web security group that has SSH and your web ports individually per server. Just create them by service, essentially, and then you can add them up on your different instances as they're needed. So in contrast to security groups, there are also NACLs, or Network Access Control Lists, and those are stateless access control lists which are applied on the subnets of a VPC. So NACLs support both allow and deny rules, and they're typically useful. Realistically, they're only useful for segmenting your subnets. You wouldn't use them as a firewall because it's not 1980 anymore. We have stateful firewalls, so don't use stateless rules anywhere you can avoid it. So like I was saying in the route table portion earlier, by default, all your subnets are connected and they're wide open. There's no control between your subnets saying, well, this subnet can talk to this subnet, but not this subnet. They all talk to each other within the VPC by default, even if they're on separate route tables. The backend networking is designed to always have your subnets connected. So that's where network access control lists actually come in, and you say, this high security subnet, only allow these subnets access to this, and don't allow anyone else to come in. And then once you've determined essentially your perimeter control around your high security subnets, then on top of that, you apply the security groups on a host by host basis to actually have your granular control. You would never want to say, you wouldn't want to use it like a normal perimeter firewall in a traditional network where you say, oh, I don't need to worry about the host firewalls at all because I'll just control everything at the perimeter level because I have a stateful firewall at the perimeter. So if you try and think of network access control lists like that, it doesn't work, especially being that they're stateless. It's just totally impractical to do a host by host granular level of network control. And they call it a deny rule. It is actually a drop rule. There is a small difference in the networking world. Deny or reject will typically respond to the client that's trying to connect, and it will say, no, you're not allowed to connect. So Amazon calls it a deny, but it is actually a network drop. So if you're expecting to get a rejection back, you're not going to get it. It's acting like a drop. Talking about hybrid cloud, which is sort of the goal of most people nowadays, or many people nowadays, especially larger enterprises. Chances are you've got either a collection of users or a collection of infrastructure on site, and you want it connected to your cloud resources. But obviously you're not just going to connect over the internet for everything. You're not going to create a SQL replication link directly to a public IP address. So you need a way to link the two together and A, make it secure, and B, also handle routing in a sane manner where you have a essentially seamless transition between your on-premise networks and the networks that are remote in your VPC. So VPC, or Amazon Virtual Private Cloud, does provide this, like I mentioned earlier. And the main way that you would do this is with the IPsec tunnel functionality of the VPC. So every VPC can have its own IPsec tunnel. So if you have different routers that you want to connect to different VPCs, you can do that. You have an individual IPsec tunnel per VPC. So if you need to route into different spots, you might have to split your VPC up into two if you needed to connect that into different locations. The IPsec tunnels are also highly available per VPC. So you get two tunnels that are essentially one tunnel, but there's actually two of them that combine together per VPC. So you don't have to worry about running two of everything in terms of VPC for IPsec connectivity. Once you've got your IPsec tunnel up, you get to use BGP with the virtual networking that is in your VPC. So if you add subnets to your VPC, they're automatically going to get advertised over your IPsec tunnel. You don't have to worry about contacting your network administrator and saying, oh yeah, we need these static routes on 10 different routers so that we can connect to our new subnets in our private cloud. It's using BGP, it's going to get automatically advertised to you, and also vice versa. If you create a new network on premise and you say, oh, now I got to go to Amazon and I got to update these static routes in all my route tables so that they know how to connect back to me, you just give it BGP and you tell it, hey, I have these new networks that you need to connect to me over IPsec. And it does the reverse too, and it'll update its routes to know how to connect those two on-prem networks. Now, what if you're thinking, well, okay, but IPsec is pretty good, but there's still encryption going on, and there's still a performance hit for that. And there's also some bugginess with MTU sizes. Anytime you're doing VPN and encapsulation, you're losing some of that MTU from your traditional 1500, and you say, okay, well, I want like real-time data replication between an on-prem database and a database in the cloud, and I know that the VPN is just not going to cut it. The latency is going to be too high. It's going over the public internet. So what if you want to go further than that? Well, the VPCs also offer a feature called Direct Connect, and this is a partner program where AWS has partnered with certain data center providers and certain companies in those data centers are authorized to actually provide layer 2 connectivity into AWS, and then with that you get essentially direct routing connectivity to AWS. It's as if you're plugging in an Ethernet cord that's about 3,000 miles long to Toronto, or whatever it is, 4,000 miles that way to North Virginia. And then you're directly connected to Amazon at the speed of light. And that private pipe that you have is dedicated bandwidth for you and you only to talk to Amazon resources. And it also lets you connect to the Amazon backbone. So even if you can only connect to a certain region of Amazon with SHA or MTS or whoever you're using to get that connectivity actually to the AWS Direct Connect partner, you can actually still connect to different regions over the AWS backbone, and you can still get that high performance networking. So if you're thinking about in Canada, if you're like us, like you're an insurance company where data sovereignty kind of matters, there's Equinix in Toronto, the Tor 1 data center, where you can connect there. There's Cologic's MTL3 data center in Montreal, and there's also Cologic's data center in Vancouver, which allow you to connect. And all of those different locations actually connect to the same AWS backbone. So you might think even if you connect to Vancouver, well, there's no AWS resources actually in Vancouver. You're connecting to the same backbone and you're ending up basically in Montreal anyways. So for somebody in Winnipeg, you would never go the wrong direction. You would just add latency. You would always want to be going the right direction based on the end region that you're trying to connect to. So I have a diagram here. This is sort of a simplistic but also complicated hybrid cloud setup, and that's very tiny. I'm sure you can't read that. But this is basically showing 3 networks in each availability zone, and then the resources around that you connect together. And hopefully that's legible enough. So what you can see there is the contrast is pretty bad, but the boxes are all shaded. So if we start from right to left, you'll see the very first object I have listed there is a IGW, or Internet Gateway, and that's basically signifying that certain networks are going to have internet connectivity. They're going to be connected to the internet. And then we've got our route table there connected to the Internet Gateway, and that's saying that we've got a route table, and that route table is going to have the Internet Gateway attached to it. So any subnets that are then connected to this route table will then have a route to the internet through this Internet Gateway that you've attached. And again, this is all virtual. You don't define any routes. You just attach these objects to the route table, and Amazon handles the behind the scenes of actually determining where traffic needs to flow to get where it's going. So then each big, large box on the top and bottom is denoting an availability zone because our subnets are their availability is within an availability zone. They're not highly available. So when you create a subnet, ideally you're creating at least 2 across availability zones, and then you can maintain network connectivity across those availability zones. So the green boxes in each availability zone, that's signifying a public subnet. And a public subnet is basically a subnet that you've defined as public. There's really no functional difference between the two. And that public subnet is then connected to our route table that is connected to the internet. And that's why we call it a public subnet, because any host that we create in these subnets that we give a public IP address will then route through that route table to the internet. So we want to keep those separate from the other route tables where when we're running applications and databases, well, we don't want those to talk to the internet. So we're going to connect them to a route table that doesn't have the internet gateway attached to it. And then we don't have to worry about security groups or NACLs. You should probably still have them, but from a networking perspective, they don't have connectivity to the internet at all. There is no connectivity, so you don't have to worry about controlling traffic more explicitly than that. You just don't attach the internet gateway, and then that connectivity isn't there. So within each public subnet, I've defined a gateway device, and that gateway device is the NAT gateway in contrast to the internet gateway. And the NAT gateways get deployed differently than the internet gateway, and this is where you need to learn about each individual gateway that you're deploying and how they differ from one another. So the NAT gateways, unlike the internet gateway, are not highly available. They're essentially an instance running in a subnet, and so if that availability zone goes down, you will actually lose your NAT gateway in that availability zone. So you might lose connectivity if one availability zone is actually routing through another to get out through the NAT gateway. You could lose that. So the highly available design of this is to actually allocate 2 of them, and then each availability zone has its own route table per subnet. That way, each availability zone is essentially independent of its other half, and then you're essentially defining 2 of most items. So then moving left, we've got we're calling it an application subnet in both availability zones. And this is where you might have applications that need to pull updates or they need to go and get data from a third party. So those subnets are connected to their own route tables. And in those route tables, we've attached the NAT gateway. So any host in these subnets is going to be able to get to the internet through those NAT gateways, but only in one direction. We don't have to worry about inbound rules because we can rely on the functionality of NAT to only allow outbound traffic from those subnets. And actually, another thing I'll mention about the NAT gateways is the NAT gateways actually rely on the internet gateway to provide internet connectivity. So each of those NAT gateways has its own external IP address, which on its own doesn't get it anything. That public IP address still needs a way to route to the internet for the NAT functionality to work. So when you create those NAT gateways, you're actually creating them in those public subnets which have the connectivity to the internet gateway. And then lastly, at the very last end of it, we're calling them persistent subnets, which is a naming scheme I have from another vendor. You could think of this as database subnets or higher value data that you want still separated from your applications. So those have their own route tables, and those route tables don't have any connectivity to the internet at all. So we're not going to let those talk out to the internet. We're not going to let anything in. They're going to be completely separated or isolated on their own. Now keep in mind, even though I'm saying isolated, all of these subnets can still talk to each other. So if you were running a host in the public subnet, that public host can by default talk to a host in any other subnet, including your persistent subnets at the end. So even though the internet connectivity isn't there, you're still only one hop away from having that connectivity to a host that does actually have internet access. So that's where things like security groups and NACLs come in to add that extra layer of security where you're not just relying on the fact that it's not directly exposed to the internet, you're actually explicitly denying connectivity to things that shouldn't have it. And then I've got in there a VGW, or Virtual Private Gateway, and that's the Amazon Gateway component of the IPsec tunnel. So we add that to the route tables as well, and then that provides connectivity over that VPN link to an on-premise data center like I showed here. You can see moving left further from that, you can see our VPN connection symbol there, and then we're connecting to an on-prem router over the IPsec protocol, and then we've got on-premise networks that are traveling over that VPN link. So in this case, over our tunnel, we would only have access to our persistent subnets. So you might say, well, just like we don't want anything going out the internet, we also don't want those internet exposed subnets routing back over our VPN link. We want them to go through one of these other subnets. So you just don't attach your virtual gateway to those subnets either, and then you don't have to worry about traffic making its way back over either. And I think that's the end of my slides. So I won't talk at you any longer. Any questions?
So I see you're recording the talk?
Yes.
It's going to be publicly available?
Yep.
Where can we find it?
There is a yet to be created YouTube channel. But I will post the link to that in the user group, the Google Groups page for this user group. So yeah, Mark will be sending out an email with. Yes. There's also a Google Groups page.
Oh yeah, that's
yeah.
It's probably you don't need to sign up as a just go.
Yeah. So yeah, I'll make sure it's posted, and we'll try and post links everywhere to get to it.
Is the fact that all of these, by default, all of the subnets can communicate with each other, is that well communicated by Amazon? Or like, could I accidentally set up this infrastructure thinking that whatever's like facing the internet is isolated, and then hey, everything's okay, right?
It's not as clear as it probably should be. When you look in your route table, you can see that they all have the same network range in them. So there's an automatically generated route in every route table in your VPC, and it's the same CIDR address that you create your VPC with, and it just says local. So if you're going in depth enough to actually look at each of your route tables and say, okay, where is this routing? You will definitely notice that, oh, that same route is in all of my route tables. But if you just click next, 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 and provision an instance, you could miss that. And then it wouldn't be super obvious that all of your hosts are able to talk to each other. Yeah.
So let's say I have a use case where I've got some backend servers. I don't want them to talk to the internet, but let's say they're Linux, and I want them to get package updates. Mm-hmm. Seems pretty reasonable. What's the best way to accomplish that?
Probably the best way would be to put, say, a proxy server in one of your app or your public subnets, and it would have internet access. And then because you've got connectivity between the subnets, you would say, yes, all of these backend hosts can talk to this one IP address in my public subnet, which would be your proxy host. And then your proxy would have access to the internet, and through your proxy, you would define more specifically what HTTP access those servers would have through the proxy.
I suppose Windows WSUS would work just fine.
Yeah.
Yeah. Okay.
Questions?
Yeah.
Thank you, Wyatt.
Thanks.